Yeah, it's your boy Chili here. Welcome to a new series that I'm going to be calling C++ Infrastructure. Today we're going to be talking about something called an inversion of control container, which is, a buzzword you might have heard. Inversion of control, dependency injection. You might not really know what it means exactly and how it is useful, but that's what I kind of want to go over in this video and maybe a few videos following it. Just a little aside, little detour. Part of the reason why I explored this myself was with respect to global services. In Hardware 3D series, I don't do a lot of globals. There's a few singletons, codecs being a main one. But for things like, for example, the graphics system, Windows, everything, those are all just passed in through functions or retained as members in objects. There is no way to globally get the graphics or globally get the windows. And in many ways, that's a good thing. But for some things, it can be kind of annoying. So less global state is a safer bet for, not creating spaghetti code, basically. But it can make things annoying, and it can make kind of your code a little convoluted when you need to get at something from a deep layer in your code. So there's a trade-off there, and lately I've been flirting with, trying to add more globals and see where the sweet spot is. And there's a lot of ways that you can, implement your global access. It's just global variables. You could organize them in a namespace or something. Using pointers, you get a little more sophisticated because you can replace them and you can have a virtual interface instead of, directly coupling to a specific concrete implementation. You go a little step higher, and you can, instead of, accessing objects or pointers directly, you can use functions to get them, and then that allows you to tie in some behavior. Deferred creation, you can put in thread synchronization if you need to. You can track access to a specific global service, and you can just keep going. And this IoC stuff, it isn't specific to global services, but it can be used with them. And that's kind of how I've been flirting with globals, is in the context of this IoC container. But at its heart, IoC container isn't about globals. I just wanted to talk a little bit about, my background and how I started experimenting with this. But forget about globals for now. Maybe we'll treat that in a future video. Right now, we're just going to focus on the core concept of inversion of control container. So let's get started. I've got a very simple project here, as you can see. The idea here is, let's say the way IoC really shines is if you have some kind of framework or library that you are, let's say, developing, and other people are going to download this framework. And it has lots of components and stuff like that in it that you can use. And the thing about these components is that, a real life framework, some of the components can be very complex. We like to compose our complex, instead of having one God object that has, 300 functions and 500 data members, and it's just some insane piece of code. We like to compose things. So we would take a large component. It's broken up into subcomponents. So component A would be our top level complex component, really, representing some big functionality. And it has a lot of functions, and it has a lot of other members, and these are subcomponents. But we're not going to implement all these subcomponents for this test here. We're only going to look at one function and one subcomponent, but imagine that there's a ton in here. All right. So it has subcomponent B, and similarly B has lots of subcomponents, but we're only going to look at one, subcomponent C, and then C uses a subcomponent D, and D doesn't have any dependencies. It's just a leaf in this node here. So if you think of this as component A is the root of a big tree, and this code here is just going down one branch of the tree. Okay. This is our framework. And we've pulled this. Maybe we pulled it off GitHub. Maybe we used VC package. but we now have this code that someone else made, and we want to use it. Okay, seems simple enough. So the function in here, do processing, it returns a string, and it is going to, basically the way this works for our little test here is it is going to call do processing on its subcomponent, add a little bit, add its own contribution, and return that. So when we call do processing here, we expect, if you were peeking at the code, DCBA, right? So it calls down the chain, D returns its contribution, C adds its own, B adds its own, A adds its own, and this is the end result string. Hopefully not too complicated. Hopefully no one is lost here. Now here's the thing about frameworks. They often do lots of interesting things for you. They're very helpful. They're very useful. But at some point, you're going to want to do something that is a little different than the way the framework does it. So you want to be able to customize the behavior of the framework. You have some options. You can either stop using that part of the framework and just write the whole thing from scratch. That's annoying. What's another option? You could directly edit the code of the framework. Change it to do what you want it to do. And what do we want it to do? Well, obviously, we need component D to morb. So we're just going to, change it to return morb. We edited the code there, and now we have our functionality that we desire. Everyone's happy. Well, are we really happy? Let's say someone releases framework version 2. It's got like amazing features. It's got huge improvements. It's tons of bug fixes. Oh, sweet. So we pull in version 2 and we replace version 1. Well, okay, now we have the upgrade, but we lost our change that we manually added. We have to now go in to version 2 and make the same change. And you might say it's one change. Well, yeah, in this simple little example, it's one change. In a real project, it might be hundreds of changes. So if you want to upgrade to version 2, it's like a huge month-long process to now go through and do all your customizations to the new version of the code. That's horrible. We don't want to be living in that kind of world. But what are we to do? Well, as writers of the framework, what you have to do in this situation is you want to virtualize all of your components. So component A, first of all, component D, this do processing function, make it virtual. Then when someone wants to, this thing might have 20 functions. When someone wants to just change the behavior of one of the functions, all they have to do is inherit from component D and override that one function. They inherit in their own code. They don't edit your framework code. Then if you ever version up your framework, they'll still be inheriting. They'll still be only overriding that one function. If you upgraded any of the other functions, they will get that upgrade. Everything will work fine. Now, when you virtualize virtual, in order to take advantage of that virtualization, what do you have to do? Well, now component C, it can't depend directly on concrete component D. It needs a pointer. So we should do std shared pointer to component D. Now, if we do it this way, if we extend component D, change the behavior of one of the functions, this one will get dynamic dispatch, and it will, it'll exhibit the behavior of the extended one. So we need to virtualize, and we need to basically own these things by pointer, unique pointer, or in this case, we'll use shared pointer. So that's going to look something like this. Now they're all owning their subcomponents by shared pointer, and all the functions are virtual. They can be overloaded if we want to extend any of these components and change their behavior. But there's a problem. Now that it's shared pointers, before it was just objects, constructor was called automatically. Now with the shared pointer, we actually have to manually construct the instances and put them in here. So now you see that we've got these default constructors here, and they just call make shared to create their dependencies. Well, I guess we would like to inherit and extend one of these guys. So we'll do class enhanced component D public component D, and we want to override. So we will do std string do processing const override, and then we will return morb. Okay, beautiful. So we've created our enhanced component D, and it's going to return morb, and everything's going to be great, right? No, we didn't. Obviously, it's not going to help. Why? Well, because these guys are hard-coded to create a concrete component B, a concrete component C, and here in component C, we create a concrete component D. But we actually want to replace this one's D with our D. So this is where the dependency injection part of the equation starts to come in. We need to be able to inject into component C its dependency. Instead of hard coding it to always create a concrete component D, we could inject anything that inherits from D. Any extension of D we could also inject into here. So we would do component C, pass in a shared pointer to component D, and then we move that into our locally stored one. Okay. All right, so we add a constructor to component C that allows you to inject a different component D. And then that will store it into the private here. So what we could do then, okay, class, that's wrong, annoying C, public component C, public, and well, we're going to replace the default constructor of this one. So now when we default construct an annoying C, it's going to construct a component C but with enhanced component D. Okay, sure. But component B, you know, it's not making an annoying C, it's making component C. So I guess we have to add one into here for component B. Takes in a C, 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 C. Okay. Geez. So now we have to create we have to inherit from component B. We'll make our annoying B that just, you know, has a different constructor, a different default constructor. And yeah, I guess we have to do the same for A. So these constructors in the framework that allow you to inject the dependencies, they're a good thing. You'll see that as we go forward. They allow you to create any one of these instances by injecting your own component instead of using the hard-coded one. But the problem is, if we want to replace something deep in this dependency tree, what happens is we end up having to inherit all the way down the dependency tree in order to replace in order each one of these classes with our own implementation. Inheriting from component D makes sense because we want to change the behavior of D. But for component C, the only reason we're inheriting from that one is just to make it construct our enhanced D. And the only reason we're inheriting from B is to make it construct our C, which constructs our D. And it's just, it's very annoying now to replace something, to replace some functionality deep in our tree. But if we do things this way, we can now create an annoying A And we should be morbing, basically is what I'm trying to say. We should be morbing, and we are morbing. So we have achieved our goal, which is we were able to extend the framework without touching any of the framework code. And now, let's say framework version 2 drops, and they add a whole bunch of functions to component D and a whole bunch of functions to component A, and they improve the existing functions so that they're way faster and way sexier. We get all that benefit because we inherited from those things. So we get all the things that were upgraded, except we replaced this one function with our intended behavior. So we achieved our main goal. We extend the framework. We customize it without touching any of the code, allowing us to upgrade it freely whenever we want. But at what cost? All this annoying boilerplate. It's kind of ugly. And it's not a great solution. So I want to show you guys a very cool way of handling this problem. Just a little demonstration. We see our customized code here. Now we pull in version 2, and in version 2, they improve the functions. And now when we pull that code in, we get the improvements together with our customizations, and we don't have to rewrite and repatch all of their version 2 code. Very beautiful. Okay, so now how do we make it sexy and remove all this garbage? Well, the main culprit here that's causing our issues is the fact that every component is responsible for creating its concrete dependencies. And if we move this responsibility to a dedicated factory that would be responsible for creating these instances, we can actually get a much better system. And let's do that. So we're going to create our class, going to call it container. And our container is a container of factories. So you can ask it, create me an instance of this static type, and it will use the factory to create the concrete implementation of that type. So we're going to need a map. So let's just put in some includes. We're going to need unordered map, and we're going to need type index because we're going to use runtime type information to generate the keys for our map, any. So std any is probably new to a lot of you, but it is an incredibly powerful tool, and you're going to learn about it today while you learn about this other stuff. So unordered map. So we're going to map from something called a type index, which is just an object representing type info that you can use as a key in a container. And we're going to map to any. So what std any is, it's basically a safer version and a smarter version of a void pointer. And you might be wondering, why do we need a void pointer? Well, stick around. So we'll call this our factory map. Okay, so what do we need in our public interface? We need two functions. We need a function to register a factory. So we pass it a factory, which is a function, and that function will return an instance of a type T. But we have a whole bunch of different types that we want to create instances for. So we need to template this function. So let's template on class T. Now the thing it takes in is a function that is going to return a shared pointer to T. All right, so let's put a little type def in here. Template class T using, so a generator function is, and let's include functional. So a generator function is a std function. Let's include memory. It's a std function that returns a shared pointer to t. So we use our templated type def here. And then, so a register factory function takes in a generator of type t. Gen. There we go. Okay, so we have a register factory function, and then we want to, at any time, be able to create instances of, a virtualized type. So template class t and std shared pointer t resolve, and we want to resolve some t. So I say resolve me a component A, and it will create me a concrete instance of component A. It could be component A itself, or it could be something that extended component A. That's the beauty. Okay. Now the trick is in implementing these. So we have our factory map. We're going to index into it type ID of t, and that will convert nicely to a type index. So we index by type, and we give it the generator t. And you see here, this is why the generator needs to be a std any in our map, because we don't have a single type for a generator. It's generator t. So we have a generator component A, component B, component C. Those are all distinct types. They don't fit into a single container unless you erase the type. That's what std any does. You turn it into a void pointer. All right. And you don't have to do address of, you don't have to do reinterpret or static cast or anything. You just assign, and std any says I will accept that, and I am now holding a generator of type t. Beautiful. Now we want to resolve. It's a little more code, but it's not that much. So we're going to const auto I, which is an iterator, factory map find. We want to find a generator for type t. So again, we do type ID of t, and if I is not equal to factory map.end, if it's not at the end, that means that we have found a factory for that type. So let's return, and here's where the std any magic comes in. Any cast, because remember, we have this container of any's. We don't know what's in there. So we have to, but we do know that we're trying to resolve a t. So the thing that's in there should be a generator for t. That is what should be in there, because that's what we stored for t. And so we cast I second, which is this. I first is this. I second is this. We cast that as a generator. Now we have a generator. We call the generator to generate our instance. Now, what if we didn't find anything in the container? Well, let's include format, and let's throw an exception. That's an exceptional option. You looked for something and there wasn't anything in there. So we're going to throw this exception. Could not find a generator for type whatever in the service map, and we call type ID on t, and we get the name of it. So we get a human readable name of that type, and we can, show the user, hey, you screwed up. Maybe think about that. Think about what you did. All right, beautiful. And here is pretty much the most basic IoC container that I can think of. Pretty simple code, pretty straightforward. It uses a lot of stuff from the standard library. If you were to code this up without any of these standard library utilities, it would be a lot more code, and you would make a lot more bugs. Learn to use your standard library. All right, so we have this container. So what? Well, let's add one more thing to the container. We're going to make it a singleton, a static container get, and then we'll create the static singleton instance C, return C. There we go. So now we can get global of this container. So what are we going to do? Well, in your framework, now what you do is you register factories for all of your components. So let's create a function. We'll say inline because it's a header. Void boot framework. Let's go auto IoC is equal to, we need to include container. Get our IoC container. IoC is equal to container get the global instance. And now we are going to register the factories for all these types. So because we're registering the factories, they're no longer going to be responsible for creating instances. So let's get rid of all of these default constructors. You're no longer allowed to default construct any of these components. You have to inject the dependencies. And that injection will be happen here. So let's go IoC.register factory. So we're going to register a factory for component A. And we'll use a lambda for that. Lambda doesn't need to take any parameters, so we can omit the parentheses. I'm screwing up with your freaking, okay. And then we just return std make shared component A here. And, well, now that I'm looking at it, I'm like, I kind of want to capture by reference so that I can use IOC dot, here's the magic, resolve component B. Haha. All right, it doesn't like it, but we'll figure that out. Why doesn't it like it? Oh yeah. Okay, so my this thing here, std function, the template parameter should be the signature of the function. This was the return. I put the return type, but I didn't put the parameter list, which is in here. Now, okay, now it's happy. So what did we do here? The factory for component A just makes shared component A, but it uses the container to resolve component B. So we're injecting this factory into the IOC container that uses the IOC container to resolve the dependency. And this is the magic that is going to make our life a lot easier. And now we just basically do the same for all the other components. So now the factory for component A doesn't hard code component B's creation. It resolves it. And for B, it's going to resolve C. And for C, it is going to resolve D. There's no hard coding of any of the dependencies. The factory function is only creating the object that it was asked to create. All the other things, it resolves them. Now component D is simpler because it doesn't have any dependencies. We don't have to get a reference to the IOC container. We just return make shared component D. Beautiful. All right. And you might be wondering, well, what does this actually do for us? Maybe you see it, maybe you don't. Bonus points if you see it, but let me show you. Let me show you. So first, let's just take a look at the case of without customizing anything. So we go back to main. Let's include, even though we don't technically need to, let's include the container. So we have our enhanced component. We don't need any of these annoying guys anymore. Because remember, components now aren't responsible for creating instances of their dependencies. So if I do component A, well, I don't have a default constructor. I'm not supposed to construct components anymore. What am I supposed to do? Auto A is equal to container get resolve. So now we resolve components out of our container. So we're going to resolve a component A. And then we can do A, because this is a shared pointer. We do A pointer to do processing. And we should return what we had before, but we'll have B but better. An exception. Okay. Could not find the generator. Yes. Okay. So this is annoying. Annoying to have to look at that in the debugger. What we should do in here is we should do a try. Catch. There. Okay. Now if we run this, it probably won't break because we caught the exception. It'll say could not find generator for type class component A in service map. We could change that. That's not really what this is. In IoC container. Beautiful. Okay. So yeah, that makes sense. Why does it make sense? Because we didn't boot our framework. So here, let's call boot framework. We have to boot the framework to register all the factories so that it can do its magic. Now that we have booted the framework, DC, B but better, A. Okay. Working as intended. So we got the same thing we had at the beginning, but, you know, quite a bit more code. Why? Well, now let's see how easy it is to inject our own extension of component D. How do we do that? Well, after we boot the framework and after it registers all its default factories, we want to replace one of them. How do we do that? Container get dot register factory. We're going to register a factory for component D and return std make shared enhanced component D. We've now injected our own dependency. We didn't have to inherit anything but the thing that we were extending. And then with a single line, we've injected it into our chain of construction. If we call this, we should see morb, C, B but better, A. We have morbed. It's morbing time, gentlemen. Bat chest. Bat chest in chat, please. All right. And there you have it. That is what it allows us to do. That is what the IoC allows us to do. We can now have this framework with this big tree of dependencies. You know, we prefer composition over inheritance. And we have composed our big system with sub-objects and sub-objects of those sub-objects. And if we want to change the behavior of any one of those objects at any arbitrary depth in that dependency tree, we just extend it. We only have to change the part of it that we want to customize. The rest stays the same and benefits from future upgrades. And then we inject it, and it gets injected into that tree, and it'll be constructed when we construct the root object that we actually want to use, which is component A. And there we have dependency injection, because in our constructors we take in the dependencies rather than construct them in the constructor logic. And with our IoC container, we have inversion of control. So the control of what dependencies get in there happens at the high level, not at the low level. And you could extend this in many ways, and I have in experiments. I've used this stuff in, you know, production code, and it's been pretty nice. I'm not certain how much I want to use it in something like a game engine, but I am open-minded on it, and I want to experiment with it further. But yeah, you can extend it. So this thing only stores generators, but what if it could also store singleton instances? Or you could have a separate service locator that depends on our IoC container. But at the end of the day, when you resolve a type, then it will generate it. But once it's generated, subsequent resolves will just return the singleton. And then you can use that as your global state management. And it's much more powerful than just, you know, a single global object just chilling out in the global space. Now, there's a lot of enhancements that we can talk about for this system. This is the simplest version, but there's a lot of features we could add. For example, these types that we're resolving, their constructor only takes in dependencies, but some objects take in constructor parameters other than dependencies. Parameters like integers for sizes or counts, or whatever, takes in parameters. We don't have, when we resolve out something from the container, we don't have a mechanism to pass parameters to the constructor of that thing. But we could add a mechanism. There's a couple of ways we could do it. We could do it statically, or we could do it dynamically with type erasure. And I've tried both. We could, like I mentioned, we could add the ability for factories for singletons in the same container. Can do both. We could have the ability to an additional tag for types. So now we could register, for example, multiple implementations of component D and add tags to them so you could select at runtime which implementation you want. So there's lots of different things that we could play around with this, but this is the basic idea. And yeah, guys, let me know what you think about this in the comments. Let me know if you understand, and let me know if you would like to see, more elaboration on this technique. I could show some of those ideas I just talked about, and it could be a fun time, but only if you're interested. If no one wants to see it, then I'm happy with leaving it as it is. But at the very least, I hope this has, given you a little bit more understanding about dependency injection and inversion of control, because it's a super important software architecture concept, but you don't see it a lot in, like just game programming tutorials. Game programming software architecture is often not as advanced for a number of reasons, but it's just a good concept to understand as a programmer in general, even if you're not going to apply it to game programming specifically. So there you have it. And as always, I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And hopefully I will see you sometime again with some more C++ infrastructure.